So the first thing we did on Friday is, I had a quick look at the topics. So this one should come first in your notes. Those of you that were away, Jory, put the phone away, please. Those of you that were away, topic 126, work and energy. That's sort of the outline for the next couple weeks. Not long. Yeah. Then I spent considerable amount of time reading through the handout on energy. I I almost gave you the first half of the whole unit in that handout, but very briefly. I didn't explain a whole lot in detail. Okay, you should read that. You should know the difference between a joule and a watt. Okay, joules measure energy, watts measure power, like watts on a light bulb, kind of thing. Okay, I gave you a couple formulas. We talked briefly about, on that handout there, where you've got the boulder sitting up on the ledge. We talked about the 3 different ways you can get it up there, and how it doesn't matter how you get it there, it still has the same amount of energy, which means it requires the same amount of work. Same amount of work. Now, what other kind of handouts do you have there? Work is a measure of how much energy is transferred. Work, it's energy. It's measured in joules. Okay. I'm going to give you some notes on work right away. Horsepower is another. It's the non-metric version of power. Watts. I think 750 watts is a horsepower, I think, something like that.
Why is it called horsepower? Yeah.
It's the amount. Well, let's just look that up. I always forget that one. All right. So what we're going to do today is we're going to have a look at some notes for work. You can jot these down if you like, and then there's a couple other handouts to go with it. And then we're going to jump right into the sample questions of work, which are incredibly easy. I think you guys will find this unit is pretty straightforward.
Yeah.
Yeah, it's pretty easy.
After you be honest with what?
Yeah, it's pretty straightforward. Okay. So, work and power. And again, feel free to jot stuff down. If you want to just sit back and relax and let it all soak in, you can do that as well. Just notes, yeah? So, work and power. Why did I start with power? That's weird. What's going on? Now I got the right one. My apologies. Okay. Work, kinetic energy, and potential energy. So here's a little cartoon here. Yeah. Is he doing work?
Yeah.
The entire time?
No.
Why not?
Rest.
What about right?
No.
Right now, is he doing work?
Yeah. He's holding the object.
You just hold it.
He's just holding it.
But he's holding
Not work.
it.
Not work.
Isn't he
I will explain. The nature of work. In the everyday sense, work involves pushing, pulling, lifting, generally physical stuff, right? And when you have a push or pull or a lift, there is a force, and there's also distance, some movement. When you push something, right? When you pull something, there's a distance involved. Not in the physical sense. Oddly enough, being a physics teacher is not technically work, unless I'm lifting heavy tests.
Yes, that's quite work. Imagine the short distance.
I'm going to tell my teacher that they don't do work. I'll probably get called out. But Mr. Bennett.
Mm-hmm.
I'm going to tell Elja that he
He doesn't know. He doesn't do anything.
Good luck with that, Zach.
You tell him he doesn't do any work. That teacher.
He'll be like, yeah, you're right.
Work is the measure of the amount of energy that is transferred. That is key. Energy must be transferred when a certain force acts through a certain distance to do some job. So there has to be a transfer of energy, and there has to be a force, and there has to be a distance. So just pushing on something and not moving, not work. Holding the barbell above my head, not work. Will I get tired?
It's still work.
No, it's not work.
Still pushing.
Yeah, but there's no distance.
Okay. Ah.
2 minutes later, does the barbell have any more energy than it did?
No.
So there's been no transfer back.
Your shoulder is-
Yeah, I mean, yeah, will I be expending energy? Absolutely. But all of that energy is going to be into like holding it up, and it's going to be the only energy transfer is I'm getting hot and sweating.
What if it falls? You know,
Goes energy downwards.
but it's still.
Is there a force applied to it? Yes, gravity.
The gravity's always applied.
So gravity doesn't work.
Gravity's doing work. Yeah,
Gravity's always working.
gravity's always working. Never takes a day off.
Can
What about normal force? Is normal force always working to do that?
As long as it exists.
Doesn't it always exist?
No. When something's falling, like Jory's phone, normal force not exist on it, right?
Isn't normal force outside the air that it's falling?
This is technically working.
But gravity's doing work on your pencil, I suppose. Yeah.
Pencil working at all.
The pencil, no. The Earth's doing it. Okay, so let's talk about.
No, it's not the earth, it's the force.
I guess, yes. Okay, so a horizontal force applied to a dynamics cart for a certain distance. Work is done because energy is transferred to the cart. The cart now has kinetic energy. So here's my cart, right? And here's my push. And after I apply a force, here's the cart over here, and I'll use the international cartoon symbol for movement. Right?
I say work is done, like, work is happening or
Work-
is done?
Work is done. Work has been
Are you
exhibited.
still working as you're pushing?
Yeah,
So it would be done,
well, that's true.
but like,
Work is being done, yeah. Okay. Now, once you push the cart and it's no longer being pushed, is work still being done? It's already moving, but is there a force? You push and let go, right? There's still a distance, but there's no force, right? Object in motion stays in motion. Does it have, if it's moving here or moving here, if you ignore friction, does it have any more kinetic energy or any less? Shouldn't, so therefore no work being done. After the push,
Work is a strong wind.
then there would be, the wind would be doing work. Even a weak wind.
Yesterday we were pushing carts.
Wind was strong yesterday, yes. And I'm sure there's probably people that leave their carts in the parking lot, right? Yeah.
Lots of them,
Idiots.
like 1,500 carts.
Come on.
Naturally. Yeah.
Note that when a force is applied at an angle, the cart moves horizontally. The only force which does useful work on the cart is the horizontal component, which is F cos theta. In other words,
First formula,
here's my cart. Well, this is just,
I don't know.
here's my applied force, but not all of that is doing work. It's just the horizontal component that does the work. What happens to the vertical component? It's pushing down, you're actually increasing friction. You are actually,
Not working. Well,
no, you're not working. You're not making it harder, you're just making it harder on yourself, right? Where does the energy go? Because energy has to be conserved. Where does that energy of pushing down go?
To the ground. Up,
Yeah.
up,
Well, into heat, right? Because if it was, say it was not a rolling thing, even if it's rolling, those wheels are going to get hot, right? They're going to increase temperature. A lot of energy is transferred and given up in temperature.
You're tired.
And I have a little demonstration for you about that very soon.
Can tire get on fire?
Can tire, yeah, that, they call that a tire fire.
They're very hard to put out.
Yeah.
Why?
I'm not sure. They have high temperature, I think. Probably burn at a high temperature.
They burn really well.
Okay, so what if I'm a FedEx guy or UPS guy and I'm lifting a box full of bricks? Because Quinn shipped me a box of bricks.
I'm gonna do that. I'm gonna ship you one brick.
Yeah.
Happy birthday.
Yeah. Have a brick. When objects are lifted, the work is done. When I lift up Jory's phone and drop it, I'm doing work. Right? A certain force is exerted through a certain distance. Energy is used up or transferred to get the job done. What are you doing work against? Like gravity, exactly.
Wait, let's go gravity, wait force.
No,
The weight force. There's no gravity, there's no work.
But don't you have to like give a little taps and in motion?
you would have to give it a little, if there was no gravity, there would have to be a little bit of force to get it in motion, but then after that, no work.
So,
Work that like
Just
Work
instant, yeah. Well, as long as you're actually pushing it, right?
we turn off gravity.
Can we, oh, if only it was so easy to turn off gravity.
is there a certain way to do that? No. Can you counteract
That goes like
that with
this.
just like opposite gravity? I got air, yes.
Guess you could go into a pool where there's buoyant force, which is upwards, right? Now, the kinetic energy of the bricks is zero. They are at rest. So if I lift up the bricks, say the textbooks, I lift them up, put them right there,
No, no.
no kinetic energy.
It was hard.
There was kinetic energy, and then I stopped. But do they have more potential energy now?
Yeah.
Sure they do. And if I raise them even higher, they've got even more potential energy, right? So where did the energy go? We say that it has been transformed into potential energy stored inside the bricks in some sort of magical, mysterious way. It's called potential energy, energy that is stored in an object because of its condition or position. Condition. Now, what would be an example of something that has potential energy because of its condition as opposed to its position?
Like a spring.
Like a spring
Or
or a rubber band, right?
break.
Yeah, they do break.
Yeah, I don't want that. It hurts.
So if I stretch it because of its position, and it has potential energy.
I know it.
Now, potential energy is all relative. It's like Thanksgiving dinner.
That was a 1.
Yeah,
That was like a 5. That was a 5. That was terrible. That was a 5. If you would have like recognized me, like, and then kept going, that would be funny. Instead of joking.
Just kept on going.
I know.
I'll have to work on it. I'll try it again. Potential energy is all relative. It's like Thanksgiving dinner.
Yeah.
So then you just laughing in my face. That's all.
Or just go like that.
If-
Liberty.
Yeah. If I drop the remote control, right, and it lands on the table, like it has a certain amount of potential energy. But because we're up here on the second floor, does it actually have potential energy right now? In some sense, in that if I could clear away the table and the floor, it would drop again. Exactly, right?
Table.
Pardon me? Or even if I just move the table, right, it would just drop from that height. So potential energy is sort of a relative kind of thing.
What is it? What happens when you drop something, it breaks and goes to another thing that breaks?
Well, the energy is used up in, pushing it apart, right? Forcing it apart.
I mean, that forces you.
When we stretch out or push in a spring, we do work on it, right? We transfer energy to it. We say this work goes toward increasing the potential energy of the spring, whether it's pushing or stretching, right?
Is air resistance considered work?
I guess, like if you were, for example, if you push a cart, right, into the wind or into any air, there's a force, the wind slows it down over a certain distance. So yeah, the wind is doing work. Where does that energy go? It goes into decreasing the kinetic energy. Where does the energy go when you decrease kinetic energy? It would probably be given off as heat. Right? Like, heat is everywhere. It's a standard answer. Where does it go? Heat. Stop slowing things down. You're causing global warming. I read on the news this morning some high school kid is suing the U.S. federal government for global warming. They're suing them because they say it's going to cause them hardship when they grow older. Good luck with that. In general, anytime work is done, energy is transferred to an object and increases either its kinetic or potential energy. Okay, so what is this magical, challenging formula for calculating work done? Well, let me show you, children. Work is proportional to the applied force. In other words, the greater the force, the greater the work. Work is proportional to the distance moved. The farther you do the work, the farther you apply the force, the greater amount of work. That's what the little fish symbol means, right? Proportional to. Work is not related to time. Whether you do a job fast or slow makes no difference. It still takes the same amount of time because it's the same job. Okay, remember the boulder going up the cliff? Okay, so work is not related to time. Okay, work is simply force and distance. So in other words, work is proportional to F times D. Work is proportional to F times D. Now, the geniuses that came up with this idea of work thought to themselves, well, because this is not, we're just defining work. Like work doesn't exist outside of our brains, really, right? Like it's just a definition of something that it's a model of how we describe how things work, right? So why don't we just define if work is measured in joules, right? We need a constant of proportionality to change it into an equation. What if we just say K equals 1? What if we measure work in Newton meters, but we define a new unit, excuse me, called the joule, and we just define it as 1 Newton meter. In other words, let's just make K equal to 1. Could we have made K equal 1,000 if we wanted? Sure, but that would have been stupid. Would have just made it harder. Make it simple. So, it's been defined 1 unit, the basic unit is the Newton meter, which is referred to as a joule, named after hairy guy.
That's a beard.
He put a lot of work into that beard.
That was terrible. I like this.
Oh. Good guy. Really very good.
He didn't use up a lot of joules shaving. He just saved it all up for thriving. Part of this. Yeah. Wanted to be in ZZ Top too.
Oh, wow.
He's dead, yeah. 1 joule is the amount of work done when a force of 1 Newton acts through a distance of 1 meter.
So what's the formula? K
equals 1, so in other words, 1 joule is the amount of work done when a force of 1 Newton acts through a distance of 1 meter. It's about lifting about an apple a meter high. That's 1 joule of energy. 1 joule. An apple a day, yeah. Keeps the beard growing.
Keeps the beard growing. I know what I would do.
Okay, so this conveniently eliminates the K in the equation, so you get, oh, it's just amazing. Is it there? Is it there? No, it's not there. I got to write it.
Oh, really?
W equals FD. I know. Well, no, I say proportional to FD, right?
Oh.
So work done is just force times distance. They made it like very easy.
Force meters, D to what?
Distance. Distance meters. A Newton meter is a joule. Did anybody go home and look on their box of vector to find out how many joules there were in a bowl of vector? No? Jordan, is there nutritional information on your chocolate milk there? Is there nutritional information on your chocolate milk? Does it say it in joules or calories? Only calories, yeah. Well, the calorie is actually another unit of energy.
Oh, what's the measure like?
Yeah, I don't know what it is. 1 joule is about.
How do you know these random facts?
Are you kidding me?
One calorie is equal to the energy used for a
gram of water, 1 degree.
Yeah.
I think it's like
You keep 1 gallon of water.
75 calories is a joule, I think, or something. I can't remember what it is. There's a conversion. Yeah. All right.
That's yeah, that makes a lot of sense. Yeah, that's good.
The amount of
Okay,
energy.
so you guys now should have, you know what, let's have a quick look at this sheet here that says calculating work done in various situations. Now, I'm not really sure why I wasted time making this sheet up because it's pretty straightforward.
He's late.
Okay?
I'm late.
But let's have a look at that.
Do it.
All right, so calculating work done in various situations. So case number 1, a force acts on a mass and it accelerates along a frictionless surface. Or if friction is present, the object might just move along at a constant velocity. In either case, energy is transferred to the mass, work is done by the force, and it may be calculated by W equals FD. So anytime you've got something moving in a force, you've got work. If it's moving at a constant velocity, then most of the work done is being converted into heat energy as opposed to kinetic energy. But considering motion at a constant velocity along a frictionless surface, once the object is moving, no force required to maintain the motion. Thus, work is 0, like Zach was talking about there in space, right? So there has to be force, there has to be distance. Case number 2, when an object is lifted vertically, work is done against the force of gravity. Note that the force needed is equal to the weight of the object mg. So in other words, if I'm lifting my mass up a certain distance d, right, W equals Fd. What F are we talking about here? Fw. And Fw we all know to be mg. And so my work done is mgd. Work done is mgd. Mass times gravity times distance. mgd.
Zing.
Not even a joke, just a formula.
No, it's pretty zing. So work equals M10.
Sometimes I refer to D as H just so I don't have to say mgd.
It's fine.
You can get over it?
It's fine.
Yeah.
There's a lot of anyone's right. No, now we're fine. Now we're
Now you're
fine.
good. Okay.
Okay, so what are we talking about? MGD. Okay, well,
All right, so when you're lifting an object against gravity, the formula for work done is mgd. What about case number 3? In this case here, for some reason, the mass is tied down. It's chained up to the wall. You can pull all you want, but guess what? Because the d is equal to 0, there's no work done. It's like Friday afternoon, no work done.
I was thinking Monday. Monday, like 10:50 o'clock.
Case number 4, a supporting force. You got something sitting on top of a pole, maybe like a statue or something.
If we got away with the weights.
Yeah. The pole exerts an upward force on the mass to support it. That would be the normal force. But since the distance moved to 0, no work done. No work.
Ever.
Hardly ever any work. What about a really skinny bald man carrying a briefcase across a room?
Yeah.
Man carries a briefcase straight out like this at a constant velocity. The only force he exerts is a supporting force. No motion in the direction of the force. In this case, in the case of the skinny bald man,
I thought he was blocking.
It has a, yeah, it has a direction.
there is, but which direction is the force?
So the case isn't moving.
The force is actually up, right? But this is the force, right? But the motion is this way. No work.
If you were to go like this,
No work.
So he's not walking.
After I've carried the briefcase across the room, does it have any more energy over here than it does over there?
you're still working.
Well, there's distance.
I'm moving, yes, but I'm not doing any work on the briefcase.
You're pushing it.
No, because an object in motion stays in motion, right?
But what about the other side?
At the very start, I'm doing a little bit to get it going, to overcome inertia. But after that, the only force done is upward. I'm just holding it. No work done.
It's obviously stupid.
It's got the same potential energy on the other side of the room as it does here. Okay? Yeah, it's a little bit. What I'm pointing out here is that the force and the D have to be in the same direction. Same idea as this kind of thing when you're pushing at an angle, right? The force and the D have to be in the same direction. Oh yeah, of course there's nothing because I haven't drawn anything. Flip the page over. Uniform circular motion. Oh, what's going on here? After 5 revolutions, 10 revolutions, etc., the body has the same velocity and hence the constant amount of energy. Thus, we conclude that the centripetal force does no work on the body. In general, there is no energy transfer or no work done when a force is exerted on a body perpendicular to the direction of its motion. In other words, same thing as the bald man. The force here is directed inwards, but which way is the D? Perpendicular. Right? No work done. Case number 6, force exerted at an angle. Oh, we talked about this already, right? You can pull in the direction of F, but the object moves horizontally. In other words, the direction of Fx or Fh. The F can be broken down into components. I've got F perpendicular at Fx, or Fv at Fx, or Fy at Fx. Right? So in other words, F perpendicular or Fy is F sine theta. No work done that way. But Fx would be F cos theta. So our work done here would be Fd cos theta, right? The horizontal component. Fd cos theta. All right. All pretty straightforward.
There's no work happening.
There's not a lot of work happening.
Well, I know this is pretty close. If you're carrying a box, that's not working.
Not working.
You should raise your work.